So we have the photon, who just wants to be free.
Mein Herr, bye bye mein Herr, auf Wiedersehen mein Herr, es war sehr gut mein Herr und vorbei. Du kennst mich wohl mein Herr, ach lebe wohl mein Herr, du sollst mich nie mehr sehen mein Herr, bye bye mein lieber Herr, vorbei. Du kennst mich wohl mein Herr, and bye bye mein lieber.
With this apparatus, you will be able to see what happens to electrons when they are acted on by electrical forces and magnetic forces that we can produce and measure. One of the things that we'll be able to determine from our observations is the mass of an electron. This tube contains a little hydrogen, and over here there's an electron gun aimed upward. The source of electrons is a heated cathode at the bottom of the gun. The electrons are accelerated upward by a potential difference applied between the cathode and the cone-shaped anode above it. The accelerating potential we read on this meter. And once we have a moving stream of electrons, we have a second way of controlling their motion, namely by a magnetic field. We know that a charge moving across a magnetic field has a deflecting force on it. We use these coils to produce our magnetic field. A current flowing around a circular coil like this produces a magnetic field at the center that has a direction perpendicular to the face of the coil and a magnitude proportional to the.
Hi, I'm Dr. Bruce DiNardo here in the physics department of the Naval Postgraduate School in Monterey, California. When a charged particle moves through a magnetic field, a force on the particle can occur. This is the fundamental magnetic force. In this video, we will present a demonstration of the effect. In other videos, we will use the concept of the magnetic force to explain other demonstrations, including a jumping wire and a loudspeaker. This is a cathode ray tube, which produces a beam of electrons. The beam is visible due to argon gas in the tube. The electrons here are moving so fast that gravity is negligible. Watch what happens when I bring a magnet near the beam. The beam deflects, which shows that there is a transverse force due to the magnet on the moving electrons. In general, any charged particle that is moving in a magnetic field will experience this fundamental magnetic force. The beam is horizontal outward. When the magnetic field points to the right, the beam bends downward. When we switch the magnetic field, switch the direction of the magnetic field, the beam bends upward. When the magnetic field is pointing straight down, the beam bends to the left. But it has to do that because we can get back to our original case by just rotating the magnetic field. That's where we started from, the beam bending downward. Finally, when the magnetic field and the beam are parallel, there's no deflection. There's no magnetic force. The fundamental magnetic force law quantitatively accounts for our observations. The force is the charge times the vector or cross product of the velocity and the magnetic field. The force is perpendicular to both the velocity and the magnetic field, and the direction is given by the right-hand rule. The force is a maximum when the velocity and magnetic field are perpendicular to each other, and it is zero when they are parallel. Let's check the magnetic force law for the cathode ray tube in the case where the magnetic field points to the right. The velocity is this way, the magnetic field is this way, the force should be up. I bring the magnetic field in, and we see that the force is not up, it's down. So what's wrong? Electrons have negative charge, which flips the direction of the force. So the magnetic force law does work here. A charged particle that is moving in a magnetic field can experience a force, which is the fundamental magnetic force. The force is given in general by the charge of the particle times the vector product of the particle's velocity and the magnetic field. What if we have the common situation of a wire that is carrying an electric current? If the wire is in a magnetic field, there will in general be a force on the moving charges and thus a force on the wire. This leads to many demonstrations and applications. We will show some of these in other videos. It is important to remember that the physics behind these observations comes from the fundamental magnetic force law, which can be demonstrated by a cathode ray tube and a magnet. Physics lecture demonstrations are always fascinating, and the quest for them never ends. This is the physics department of the Naval Postgraduate School, and I'm Dr. Bruce DiNardo. Thank you.
Again, back to my paper. As you recall, I stated that Einstein's colleagues and physicists at the time when he published his theory of general relativity believed that gravity was indeed an electromagnetic wave. And contrary to the contemporary belief that Einstein's theory of relativity changed the whole landscape of gravity, that notion is incorrect. And Max von Lowe, in Inertia and Energy, clarifies that Einstein's theory of general relativity did not change the basic concept that gravity was electromagnetic. It just basically redefined in geometric metrics how large masses in the universe cause energy wells or gravity wells to accumulate, around which photons would travel at the speed of light in order to conserve energy. So photons, rather than going through the blockage, which is the electron matter of the Earth, will instead hit the Earth, and instead of going into the Earth, it will deflect off and go around the perimeter of the Earth. And that is because photons, by their very nature, have less energy content than the heavy electrons that are making up the atoms that constitute the Earth. Photons, as you know, are light. They travel fast, and they want to hitch rides on other energy sources in order to take a ride. They're hitchhikers. For example, an electrical wire. It's basically made of electrons. And so the photon, instead of just jumping all around, will suddenly focus itself on the electric wire and say, hey, why don't I hitch a ride with the copper wire? Go down there, and the electron sine curve is not going through the negative charge copper. It's actually floating just above it as it hitches its little hand to that copper wire and goes for its sine curve waved ride at the expense of the copper wire. It's using the copper wire's electrons to boost its own speed. So here Max von Lowe, in Inertia and Energy, emphasizes that Newton does not equate gravity to mass with acceleration, but the rate of the change of momentum. Gravity has a linear momentum, resting velocity, and an angular momentum of torque that produces the flux, which is the emission of excess energy that produces the accelerative force felt by opposing objects. This net excess energy is proportional to the difference in mass of the two bodies and their distance. When both bodies achieve, we're talking about electrons here, when both electrons achieve their net energy proportional to the difference in the mass, the two bodies and their energy produces an accelerative opposing force. It goes on to talk about how the flux is still the accelerated force, etc., etc. Now, the paper I produce is over 55 pages long. It's complex. It tries to answer so many questions at once. You're going to have to do your own study. But don't take my word for it. This is Max von Lowe saying that the theory of relativity didn't throw out Newtonian physics at all. It just refined Newtonian physics and the geometry of space. I'm not the only person that's been beating their heads or their chests with their hands saying, wake up the Brian Greens of the world. Einstein's general relativity does not equate gravity with the curvature of space. The curvature of space is the result of the waves of gravity extending and collapsing the fields of gravitational waves. But here's another fellow, a scientist. He published this in Phys Ed, and basically here's his abstract, Einstein's gravitational field. The abstract, there exists some confusion as evidence in the literature regarding the nature of the gravitational field in Einstein's general theory of relativity. It is argued here that this confusion is the result of a change in the interpretation of the gravitational field. Einstein identified the existence of gravity with the inertial motion of accelerating bodies, i.e. bodies in free fall, whereas contemporary physicists identify the existence of gravity with space-time curvature, or tidal forces. The interpretation of gravity as curvature of time-space is an interpretation Einstein did not agree with. So let's go on down to this. The author is Peter M. Brown, and it was a scholarly paper, peer-reviewed, and he goes on to say basically what he just said in his abstract, that Einstein never identified gravity with the curvature of space-time. The space-time curvature and tidal gravity are the same thing, expressed in a different language. However, one of the main tenets of general relativity is the principle of equivalence. A uniform gravitational field is equivalent to a uniformly accelerating frame of reference. This implies that one can create a uniform gravitational field simply by changing one's frame of reference. Thus, according to the interpretation of gravity as a curvature in space-time, it becomes a contradiction in terms. The apparent contradiction is obviously quite confusing. Goes on and says it's confusing. I didn't find it confusing when I read Einstein's paper on general relativity, but hey, there's been 100 years of people confusing what Einstein meant. And like I said, Einstein later on also got confused. But anyway, his paper goes through and talks about that, basically this wasn't a change in interpretation of gravity being electromagnetic fields and conforming to electrodynamics. It was simply talking about how frames of reference can change how somebody is viewing an electron. So Einstein famously used the fact that a man standing at the side of a railroad track sees a train go by, and say the train is traveling at close to the speed of light. He's going to just see 8 because he's standing on Earth, and the train is accelerated at the Earth's speed plus an additional speed of, let's say, let's use a modern day train. Let's say it's 150 miles per hour. So you've got the Earth's velocity, and then you've got the train's velocity that's added to it. But the man is standing only on the Earth's velocity. So that man is going to see the train go by in a whiz. It's going to be a whiz, right? Because that train, it contracts, and it becomes like just a short little train, fat, and it goes whiz by. That's because the man is standing on the Earth, and the man is not accelerating. But the train is accelerating at 150 miles per hour plus the speed of the Earth. Okay, and then Einstein uses in his general relativity that the man sitting in the train, traveling at that time, the Earth's velocity plus the train's velocity, he has become balanced or become in equilibrium with the additional velocity of the train. So basically, while he's sitting in his train compartment, he doesn't feel gravity because he's become equalized with it. He's become equalized with the additional acceleration of 150 miles per hour. So as that man sitting in the train does not feel any additional force on him, he looks out at the man standing beside the train track, and he just sees a man just standing there at his own leisure as he's peering from the train. Well, the man standing on the train track just sees the man in the train whiz by, whiz by. And that's what Einstein's theory of relativity states. That if you're standing in the same gravitational force field, which is Earth, those two bodies that are traveling, one at the speed of the Earth, the other at the speed of the Earth plus 150 miles per hour, they're going to look different to each other. Both are going to feel like they're at rest, but the man standing on the train track is going to see the train go by in a whiz, and the man in the train compartment is going to look at that man standing there and go, oh, hello. He's going to be waving to him as he goes by, just leisurely waving to him. And the man on the train track can't even see the guy in the window because that train has just flashed by. He doesn't even have the opportunity to see the man in the train track. And that's basically what Einstein was trying to discuss, how time dilates or contracts depending on our relative speeds to each other within the gravitational field of the Earth. Okay, it doesn't mean that acceleration is equal to speed or anything like that. It's trying to explain a different concept. He did not throw out Newtonian physics. In fact, all the electrodynamic constants, including Faraday, including Maxwell, have been incorporated in all other particle physics interactions, such as Lorentz transformation, Dirac equations. They're all electromagnetic equations and constants based on electromagnetism of Faraday and Maxwell. So let's look at one of Einstein's paper. This is entitled Relativity, the Special and General Theory, 1920. He calls it the gravitational field. So Einstein was short, always to the point, used very few equations that I can't even understand. But anyway, let's just go to the meat of it. Basically, Einstein is saying force equals inertial mass times acceleration. Do you understand? He's saying there's still a force. It's the inertial mass, or that magnetic moment of the electron, times its acceleration, how fast it moves. Okay, so then he goes on to say force also equals gravitational mass and the intensity of the gravitational fields. So he's just using a different thing right here. He's saying you still use the mass or the weight or the energy content, say it's the Earth, and the intensity of the gravitational field. He's talking about, and then the content of the gravitational field as it wells up around it, as it focuses, as it concentrates around it. That's a different way of saying the same thing. So he just kind of added a different way of looking at it, but meaning the same thing. So you can't just say that's curvature of time and space, because intensity of a gravitational field is meaning a specific thing. It's meaning a density, a focusing, a contraction under a torquing effect of the gravitational field underneath that additional mass. Hey, same thing. It doesn't say that there's no force. It's saying that that is a force, not what the Brian Greens of today are saying, which is there's no force of gravity. It's simply a ball rolling down a hill. No, a ball doesn't roll down a hill because the ball rolls down the hill because the force of gravity and the intensity of the gravitational field, which is condense or contract underneath it because it is torquing, and it's getting shorter, and arcing, that pulls that ball downward. So, and this is Einstein explaining his own theory. He just used a different equation. I don't know. I think that's kind of brilliant. A different way of explaining the same thing. This is someone else's equation. I'm sure you know who it is. Maxwell, or I don't know right now. But then he created his own equation, which means the same. Like, it's the same as saying E equals mc squared, or you can say mass equals E over c squared. I mean, there's different ways of writing equations on the different sides of the equal sign. This is all Einstein did here, was write an equation differently, but meaning the same thing. So here's his new equation, which is, why do we need it? I don't know why, but he seemed to think we do. Well, it does indicate the geometry of the space of the gravitational shortening and gravity wells within space. But then he says, if now, as we find from experience, the acceleration is to be independent of the nature and the condition of the body, and always the same for the given gravitational field, then the ratio of gravitational to the inertial mass must likewise be the same for all bodies. The gravitational mass of a body is equal to its inertial mass. Now, where does that indicate that Einstein changed any of Newtonian or electrodynamic theory? It doesn't. He's using inertial mass, which is a magnetic moment or angular momentum, and saying the gravitational mass is equal to the inertial mass. When did everybody lose their way? When did the Brian Greens of this world lose such a simple concept? So, based on 100 years of misinterpreting Einstein's theory, we get videos such as this one, a Gila science video. And let's listen to all the errors this video makes.
Isaac Newton's universal law of gravitation represents a quantum leap in human understanding of the forces that define the universe. Newton published this law in the late 17th century. He asserted that all objects attract one another and that this force, gravity, was responsible for holding the planets in their orbit around the sun. He had discovered the force that holds the universe together. Newton's force of gravity acted upon any object with mass, but not on massless entities like light. 200 years later, another
Okay, let's stop it right here, because that's wrong. Light is massless in its resting state, but all the scientists, von Lowe, Dirac, everyone agreed. While in its resting state, a photon is massless. Once it starts to accelerate, it has inertial mass and can interact with other atoms and electrons. If it didn't have inertial mass, it would be non-interactive with matter. So,
"200 years later, another great mind was pondering gravity. In October of 1907, Albert Einstein was working as a patent clerk in Bern, Switzerland. Between patent assessments, he was thinking about gravity and the fact that weight disappears during the acceleration of free fall. Jump off of a tall building and your weight disappears. You do not feel the pull of gravity on your body. You have become weightless. Where did the weight go? Or to rephrase the question, where did gravity go? Einstein's suspicion was that gravity had become something else. He believed it had become acceleration. Gravity and acceleration were equivalent. Later on, Einstein...
okay, I'm going to stop it here. That's not anything that Einstein said. I never saw this in any of his papers. I haven't read all of his papers, but I have read general relativity. Now, basically where gravity went, shall we say, is electrons can absorb up to 25% of their mass in angular momentum. So in free fall, the human body can equalize itself to the terminal velocity of falling to the earth. And so you don't feel gravity because you've equalized with it. But when you do feel gravity and you feel its force is when you hit the earth and all your little electrons and all your little atoms explode because they can no longer hold their structure because the energy of that impact has just exceeded the electron shelf or the atomic nature of the density, which is 25% of c squared. Once it exceeds 25% of c squared, your history. No more structure, no more body.
Isaac Newton said that an apple falls because a gravitational force accelerates it toward the ground. But what if it's really the ground accelerating up to meet the apple?
I just wanted to leave with my favorite genius not explaining, I guess, that the earth travels up to the apple. I think this guy is great. He's funny, he's got energy, but oh my goodness.
Suppose I drop an apple. According to Isaac Newton, the ground can be considered at rest. Earth applies a gravitational force to the apple, and that force causes the apple to accelerate downward. But according to Einstein, there's no such thing as a gravitational force. Instead, it's more appropriate to think of the apple as stationary, and the ground, along with everything on the ground, as accelerating upward into the apple. Now, what I just said sounds preposterous and maybe even moronic, but it's not sophistry. There's something substantive here, and today I'm going to clarify what exactly this point of view means, why Einstein came to adopt it, and how it planted the seeds for what would eventually become general relativity.
There could be many reasons why people have misinterpreted Einstein's theory of general relativity. Some may have been mistaken, but I can't believe that this big blunder was not done with some kind of intentional purpose behind it. And I'm not going to say what that is, but it's the same thing with social experiments or psyops or whatever? Was there some kind of design underneath the deflection from the actual celestial mechanics of the universe that we had discovered up until 1915? And then since 1915, nothing new has been discovered about the celestial mechanics? I don't know what that intentional deflection or distraction could have been, or what sleight of hand was going on. But I know that there's always one general premise that you can always rely on, is you need to follow the money.
Money. Money makes the world go round, the world go round, the world go round. Money makes the world go round, it makes the world go round. A mark in a buck or a pound, a mark in a buck or a pound is all that makes the world go round. That clinking, clanking sound can make the world go round. Money, 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 money. If you happen to be rich and you feel like a knight, entertainment you can pay for the escapade. If you happen to be rich and alone and you need a companion, you can ring ting-a-ling for some mate. If you happen to be rich and you find you are left by your lover and you moan and you groan quite a lot, you can take it on the chin, call a cab and begin to recover on your 14-carat yacht. What? Money makes the world go round, the world go round, the world go round. Money makes us go round, I'm glad we both are sure on being poor.